Okay, hey everybody, we are back with the second in our two-part series of Intro to R programming in preparation for Bioinformatics 527 for fall 2020. And today we're going to be talking about some more complex data structures. We will also get into what packages are in the R programming world and how we can take advantage of them. And we will do some fun things like we'll make a heat map today. So yeah, so let's get into it. Get rid of this. And all right, so let's do a little recap, remind ourselves what we went over last time. We were talking about, well, a couple of key points actually, and they're both sort of epitomized by these quotes from John Chambers. So what John Chambers says about the R programming language is that everything that exists is an object, and everything that happens is a function call. And so that's good news because we learned how to create objects in R last time using this assignment operator. So we've got the assignment operator here, which is sort of this hacky arrow. And if we put an expression on the right side of this arrow, we can store the results of that expression into a new object that's named virtually anything we want it to be named. And then we can carry that information around in that object for further use. We also learn the general syntax for calling functions in R. So not only can we create objects, so everything that exists is an object, we can create those objects, we know how. We also learned the syntax for calling functions. So we can create objects and we can call functions. And the way we call a function in R is to use the function name. And then inside of parentheses, we just feed that function the arguments or the pieces of information that it's going to need to do its job. We also learned about data types last time. So data types are this extremely important concept in R. All objects in R contain data of a particular type. And a data type describes what kind of data an object holds. So examples of data types that an object may hold were numeric. That one's pretty straightforward. Character, which you're familiar with. And the key here is anything inside of quotes, even something that looks like it's numeric, will be considered character by R. And then we've also got a data type called logical, and the logical data type is completely made up of the values true and false. And then finally, we have the factor data type, and factor data types are really useful for doing grouped and subgroup analyses. They allow us to group all of our samples based on a condition, like tumor versus normal, treated, untreated, and so forth. Okay, so in addition to data types, there's another really important concept in R programming in general, and that is data structures. So all of our objects are going to contain data of a particular type, and all of our objects are going to have a particular structure. And when it comes to R, there's these four sort of most common data structures: the vector, the list, the matrix, and the data frame. And we heard about vectors last time. They are a very straightforward data structure. They're one-dimensional and they contain a single data type. So we looked at numeric vectors and character vectors, and they contain one data type, which is indicated by the color here being all blue. Every element of this vector it has the same data type. And then today we're going to get more into data frames. So we're going to be talking about data frames and how those are different from vectors. And we looked at how we can work with vectors. So we saw how to create vectors. So we got some experience with really our first function that we spent a lot of time with, which is the C function, which stands for combine or concatenate, and it lets us smash things together into a vector basically. And so we can say C of 1, and then using the colon operator, all the values from 1 to 5 inclusive, and we can put that into a vector. We could create another vector with the C function, anything we want. And we created these numeric vectors, and we saw how we can use arithmetic operators on those. And we got to see how vectorization works, and we sort of got an appreciation, hopefully, for how that can be a useful characteristic of the R programming language. We made some character vectors as well. We saw that you can't really do math with character vectors, which is the first example that I wanted to show of how you really have to know what type of data you're working with. And what that data type how it works with different functions. And we, ran into some useful functions like paste, which allowed us to make all these labels in one line of code very simply. All right, so let's get into some new material. So for today, that material is going to revolve around the data frame. So vectors are those one-dimensional data structures. Data frames are two-dimensional data structures. And importantly, data frames can hold multiple data types. So a data frame is actually made up of vectors. So in order to create a data frame, you need vectors that are all of the same length, and you can put those same length vectors together into a structure called a data frame. So by putting together vectors that are of the same length together in a data structure, you get this rectangular data structure called the data frame, and it can contain different data types. So that's shown here by the different colors. So you could have a data frame where one of the vectors, which makes up a column of the data frame, is numeric. Another vector that makes up the second column might be data of type character, and the third column might be made up from a vector of type logical. And we looked at a data frame. We didn't really talk about it as being a data frame at the time, but the iris data set was appeared in our environment. We brought it into our R environment, and it is a object, and it is a data frame object. And so the iris data frame has 5 columns, and this is what it looked like. And we can see that there are 4 columns that contain numeric data, and then the 5th column actually contains data of type factor. And data frames, as you would imagine, I'm sure you recognize them, are really the most common way in which we're going to encounter data as research scientists. It's basically a spreadsheet, right? And so we're going to work with data frames all the time. And with that in mind, it's important to know some terminology when it comes to data frames. So, you'll hear people refer to columns and rows of a data frame, but just so you're aware, people will also refer to a column of a data frame as a variable, just like they will oftentimes refer to generally an object in R as a variable. So it's just, it's a little bit of terminology to get used to, and the lines there get a little gray sometimes with the way that people use it. But just get used to that. If you hear someone referring to a variable of a data frame, they're referring to one of the columns. And likewise, they may, instead of calling a row of a data frame, they may be referring to them as observations. So a data frame will have variables and observations, or columns and rows. Objects in R also have attributes. Attributes are something that is beyond the data itself that the object holds. You could think of it as metadata or information about the data that is not the data itself. And when we're talking about data frames, attributes for data frames, so we'll have the data here, and then attributes of the data frame of this structure are, for example, column names. So they aren't the data itself, but they describe what's held inside the data frame. And another attribute, an example of an attribute for a data frame, are the row names. So again, not the data, but part of what describes that data. And so let's go and let's get RStudio going. So let's get that fired up. Instead of me just talking, let's do writing some code. And let's see, I gotta go get R open. So I'm going to launch RStudio. We're going to use our handy dandy IDE to do all of our R programming. And whenever we open up a session of RStudio, again, that first thing we're always going to want to do is go to Session, Set Working Directory, and choose Directory. And just like last time, I'm going to go to where I'm storing those 2 files that we're going to be using, and we'll make more use of those today. The Alzheimer's.csv and the rep1.txt files. And then once we find that directory or that file in your file system architecture, you just want to hit open. And the code for accomplishing that, setting your working directory, is actually accomplished through a function called setwd. So we could have typed all that out, and this is just the location in my personal file system where that directory is. As we did last time, we can always say list.files and take a look at what's in there. For you, importantly, what you should have are Alzheimer's and rep1.txt. All right, so once we've got our working directory set, then we're going to grab a script. So we really don't want to be writing code down just in the console because we can't keep it. It will just disappear. So we want to go to File, New File, and we're always going to grab a new R script. And just like last time, we're going to bring the iris data frame, which is it's called a built-in data frame. It's always available to us. We just have to call on it, basically. And R has a bunch of these, and they're useful just to play around with if you're learning new functions or want to just test out a new function on a data set that you're really familiar with. And so the iris data set and others can be really useful. And so we'll just run that line. Now we've got iris in our environment. And let's try this new function, attributes, and we'll call it on the iris data frame. And what do we get from that? So we see that we can now, when we call attributes and we feed an object, so the attributes need some object as its argument. And when we feed it the iris data frame, it's going to go and show us not the data itself, but what are the attributes for that object. And in this case, we've got a data frame, so it's telling us the column names, the class of this object, which is a data frame, and then all of the row names. So that's how we can get to the attributes of an object. So something to be aware of, that in addition to the data and what the object is holding itself, it will also have something called attributes. Okay, so how do we create data frames? So we know how to create vectors. We got comfortable with that last time. The way we create a data frame is, we need a collection of vectors that are all of the same length. They can be of multiple data types. And then we just use a function that's appropriately named data.frame. And we can use that to put all of those vectors together, whatever they are, into a new data frame. And so in this case, we're going to use paste 0, which I think we saw last time. Maybe not. It's a variant of the paste function that's just going to smash this character data together with these values and create a new vector. We'll grab the numbers from 101 to 110. And then we'll grab 10 random normal values. So let's go ahead and do that. So for the A vector, we're going to say paste 0, and we're going to paste sample onto the values 1 to 10. So let's run that. And then we'll take a look at A and see what's stored in there. And indeed, there we can see sample 1, sample 2, sample 3, and so on. For B, we're just going to grab the numbers 101 to 110. And you can see that you don't even need the C function. When you're working with numeric data and you just want a series of whole numbers, if you just say the first and the last value and separate them by the colon operator, it will know that you want to grab all of those values as a vector. And so we can run that, and we can take a look at what's in that object, and there they are. And then the last thing we'll do is we'll use that rnorm function, and it just needs the only argument we need to feed it is how many random values we want from the normal distribution. And so we're going to ask for 10 of those. And we'll see which numbers I got. You should get different values because it is random. Okay, so now we've got 3 vectors that are all of the same length. And so we could create a data frame now. So we could say mydf, and we just call that data.frame function. And we feed it, the arguments that it's going to need are what are the vectors. So if we're creating a data frame, we know we need to feed it vectors. In this case, we've got this A, B, and C. And we'll run that. And then we can take a look at what is stored in mydf. And there we go. So now we have a data frame that we just created from scratch. And so that's how you go ahead and manually create a data frame from some vectors. There's our data frame. But that's not really how we're usually going to be getting data frames into our environment. It's not often that we're going to manually create a data frame. It's usually going to be data that either we've generated in the lab, that we've gotten from some core facility, or that we're grabbing from a public database, maybe downloading from someone else's publication. Regardless, it's always going to be a file that's either housed locally or that we're getting from a database, or grabbing from somewhere on the internet. So how do we do that? And because that's really how we're typically going to be bringing data frames into our R environment. So let's look at how we do that. And the way we're going to accomplish that is through a very useful function, a function that we'll use all the time, called read.table. Okay, and read.table allows us to read local data sets from a file into our R environment. And so there are 3 arguments that we have to feed to read.table in order for it to do its job. The first is an argument called file, so it needs to know the name of the file that we want to bring into our environment. The second argument is going to be the header argument, so we need to tell read.table, is the first row of this data set column names? So that would mean that it does have a header. If that's true, we would enter the true, the logical data true. If there are no column names, if the first row is just data, then we would say header equals false. And then finally, we need to tell read.table what is the separator. So how does it know where one column or variable begins and ends in this data set? And so if we have a comma separated data set that we're trying to read in, we would just say that the sep equals the comma. So read.table is a great function because it's really flexible. You can read in data sets that are delimited in any way, so tab, comma, space, something more exotic. As long as you can figure out what the separator is, you can read it in using read.table. Read.table has many possible arguments, but typically the only things we need to feed it to get what we want are these 3 arguments here, so file, header, and sep. And now that we're getting more comfortable running functions, I wanted to mention that that you can import data in a couple of different ways. So I've actually got another typo here that I'm realizing. Oh no, I don't. Okay, sorry. So I take that back. So here we're just going to be reading in cell cycle rep1, which is the rep1.txt file, and Alzheimer's using read.table, right? So we'll get to what I was thinking of in a minute. So let's go ahead and do that. So we're going to have to create this new object called cell cycle rep1. And we will use read.table, and the first argument is going to be the file argument, which in this case is rep1.txt. It indeed does have a header, and in this case it's a tab delimited file. So we're going to use the \t as the separator, which in R, that just is how you indicate a tab. And so that's our separator. And we'll do something very similar for the Alzheimer's data set. Except this is a CSV file, which means that in this case our separator is going to be the comma. So let's go ahead and do that. Let's go grab these 2 data sets and bring them into our environment. So I believe we're calling that first one cell cycle rep1. And then we're just going to make a call to read.table. And we're going to say file equals rep1.txt, header equals true in this case, and our sep is going to be \t. And if we run that line of code, voila, there is our data frame that we've now brought in from a local file located on our computer. And we can do the same thing for Alzheimer's with a call to read.table. In this case, we'll be saying file equals Alzheimer's. Our header, it is true, it does have one, and then our sep in this case is the comma. Okay, and there's the Alzheimer's data frame. There it is, we just brought it into our environment. So now we can actually do something with this data, analyze it using all of the power and functionality of our programming. And so, it might seem kind of annoying that you've got to write that code, which might seem like a lot in order to just read in a file. We're used to just clicking on things to open them up. But I just want you to keep in mind that this gives you programmatic access to data files. So, if you're just opening one file, yeah, it's fine to go and double click on something. But what if you're opening 100 different files and you want to put them all into one data set? You're not going to want to do that manually. And being able to programmatically read files in, knowing how to combine things, which you've already seen a function that does that for making vectors, and there are ways to do that with data frames. This gives you, puts a lot of power at your fingertips. So just keep that in mind. And really calling read.table is actually quite straightforward once you get used to it. I want to mention that you can also read data in directly from the internet if you have a link to a data set. So this is just an example of doing that. And instead of feeding the file argument, the name of a file located in your working directory, you're actually going to feed it the link to that data set. So we can go ahead and just, I'll show you how you would do that. So here's a link to a bunch of different data sets. And if we go here, eventually, maybe we won't be able to get there today. All right, we'll try that one more time. All right, well, we'll skip that for today. If you go to this website, typically, I must be having a connection issue. There's a bunch of data sets. You just right-click on any of them to get a link to that data set, and you can read them in right from the internet. So you can go ahead and grab any data set there that's available in that database. All right, so again, we're getting more used to calling functions. So another really useful thing to know about functions is that you can always get help on a function. So the way we get help in R on a function is by typing the command question mark and then the name of that function. So let's go ahead and just look at what we get from question mark read.table. I'll run that. Okay, and so here we can see down in the lower right panel on the RStudio interface that we've got all the information we sort of would ever want to know to get started with read.table. So we've got it actually tells us where it comes from, which we'll talk about this in a few minutes, and then it describes what this function does, and then it's going to tell us what are all the arguments that are possible for read.table. And then if we scroll down, it's going to actually, for each of those arguments, it's going to tell us exactly what those arguments are and what the function is expecting when we enter information for those arguments. So let's jump back here. And so let's look at this. So there's actually a lot of information here, and it's maybe a little overwhelming because it's kind of a wall of text. But the key thing to know is when you're looking at a function and you're looking at the help documentation, which is what we're looking at here, and we're looking at the arguments, that there are two types of arguments for a function. One are required arguments. The other type is optional arguments. And so required arguments are going to have no default value. So these are arguments where the function needs you to provide some information or you will get an error. It will not run. The optional arguments so file is an example of a default, or I'm sorry, of an argument that's required. It's got no default. If you don't tell it what file you want to read in, there's no way for this function to know what file you want. However, header, if you don't give it any information, there's a default value, so it will assume that the header information is false if you tell it nothing. And so that's an example of an optional argument. And so you can see there's a ton of optional arguments here that will let you modify how read.table works in a lot of potentially interesting and useful ways. But as I mentioned before, in many cases, we're only going to need this required argument, and then we typically want to tell it whether or not there's a header and the separator, because if we don't tell it anything, it's going to assume that the separator is an empty character. An example, here's an interesting argument here. You might have a data set where the first, say, 10 rows are some text describing the data set. So maybe when you're reading that particular data set in, you're going to need to take advantage of the skip argument, where you're going to want to skip those first 10 rows of text in order to get to your header or your first row of the actual data set. And so that is just an introduction to required and optional arguments taking a look at read.table. Okay, and this is what I was thinking of previously. So another thing about calling functions is you can be very explicit about how you feed in your arguments. So you could say read.table, file equals rep1.txt, header equals true, sep equals tab. Or more of a shorthand way to do it, and you'll see people writing their code like this a lot. They will actually omit the argument names. And if you just feed the argument, the values into a function in order, the function will assume that that's what you mean. So if you don't name the first piece of information you give, it will say, okay, I'm assuming that this is for file, because file is the first argument of that function. And the same is true for the header. I didn't say that the header was true here, but since it was the second piece of information I provided, and header is the second argument for this function, then it just assumes that's what I mean. So these two lines of code are absolutely equivalent. And if you run them, you'll see you get the same result. In both cases, you will bring in rep1.txt into your environment from your working directory. I really like writing code like this in most cases, just to be explicit. And so you and anybody reading your code knows exactly what you were doing, but you run into this a lot. And I fall into this habit, and you will too in some cases. You just get really used to a function, and you'll stop writing out the arguments in that way. Okay, so now we know how to create objects, call functions. We can bring data into our environment from our local file system. We can grab stuff from a database if we have a link to it. The next big concept in R that we're going to want to work on is subsetting. So now that we can bring data sets into our environment, the first thing we often want to do is to subset or slice and dice these data sets. And the reason for that is we might want to just do a focused analysis on particular slices of that data. We might want to break it up into multiple data sets. I mean, it's something we're just always going to want to be doing with our data frames. That will become clear as you work with data in R. And there's a lot of different ways to do this. So we're going to get started with one way today, one of the more common ways to accomplish this. And so let's take a step back and let's start subsetting, not with data frames at first, but let's just do some subsetting with vectors. So that's a simpler data structure, so it's a good place to start. And the way that we actually can subset vectors in R is through the use of something called square bracket notation. So we use these square brackets. And that will allow us to subset a vector. And I do want to mention that this does tend to be a source of confusion for new users as we go on, but hopefully we'll take it sort of step by step here, and hopefully it'll make sense. But it can be like the first place where people will stumble a little bit. You might have to do a little practicing to sort of ingrain this. And so how does this work? So square bracket notation looks like this. If you've got a vector, you would name that vector, and then inside of square brackets, you would just say what elements you want to extract from that vector. And so what do I mean by that? Well, here's a numeric vector that's just sampling the values 1 to 100 10 times. So here are the values that came out of that line of code. And we can say, I want from that vector, inside of square brackets, if I just want the 6th element, I can just put the number 6. And so R is going to know that that's what I want. So it's going to go 1, 2, 3, 4, 5, 6. It's going to grab the 6th element from that vector, and that's what it's going to give back to me. Similarly, I can say I want the first 3 elements of that vector, and it'll grab the first 3. If I wanted, say, the 1st, the 3rd, and the 5th, well, I can feed a vector of those values by creating that vector with the C function and saying, okay, I want the 1st, the 3rd, and the 5th element, and it will do that. You can also use negative values, so you could say, I want everything except the 10th element of that vector. And so that's what negative 10 would mean in this case. So let's go and we can just do that together. So let's do my numeric vector. And we'll call the sample function, and we're going to sample the values 1 to 100 10 times. We'll run that. Let's see what we got this time. Oops. All right, and there's the values that I got this time. And so now let's imagine that this vector is something interesting, and we want to subset it in some interesting way. And so we can just grab, the 6th element, and there it is. In this case, it's 54. We could go back up and say I want the 1st through 3rd element, and there they are. If we want the first, the third, and the fifth, we've got to feed it a vector of those values. And there's the first, the third, and the fifth. And we could also grab everything except the 10th value, and we'll get everything but the last one there. Okay, so that's square bracket notation and how we can use it to subset vectors. So most of the time we're not going to be typing in numbers into square brackets in order to do subsetting. We're actually going to be taking advantage of the logical operators that we introduced last time. And so, how does that work? So if we have a numeric vector like this one here, we can use a logical operator and get some information about that vector. So let's say we're interested only in the values of the elements of this vector that are greater than 50. So using this logical operator, we will get back a logical vector. So now this is a vector with data of type logical, and it's telling us wherever it says true, that means that this vector contained a value at that element that was indeed greater than 50. So the first two cases, it's true. The third case, it's 13, false. The fourth case, just missed, but that's false. The fifth, there we go, over 50, and that's true, and so on. And so we can take advantage of these logical operators in order to subset the objects that we're working with in interesting ways, ways that are useful for us. And so let's take a look at that. So, we can do something like we just looked at. And if we look at just what the result of that is, there's that logical data all in a vector. And so, we could call that. Okay, and so now we have all of that logical data inside of that vector, and so we can actually use that information for subsetting. And so this is where some people will get tripped up when they're just starting out. But I can say my numeric vector, and now inside of square brackets, instead of typing numbers, I can use that logical information contained within that vector to tell square brackets which elements I want. And it's going to take any element that has a value of true in the logical vector. So it's going to go through and just grab all of those instances. So and I called that my logical vector. So I can actually use that for subsetting now. And there they are. There are all the values that are greater than 50 from that numeric vector. All right, so like vectors, we can subset a data frame using square brackets. And so as you can imagine, you've got to give it two pieces of information now. So with a vector, you just need to know which elements you want. With a data frame, we need to tell it which rows and which columns because we've got a two-dimensional data structure here. So I think that makes sense. So just like we can with vectors, we'll say Alzheimer's, and then inside of square brackets, the first piece of information is always going to be the rows that we want. And that second piece of information is going to be the columns. So we'll just say in this case, I want the first 10 rows and the first 5 columns. And so let's go do that. See how that looks. So there's Alzheimer's, and we'll say the first 10 rows and the first 5 columns. All right, and there it is. So we've just subsetted out from the whole Alzheimer's data set, which has 333 rows or observations and 132 columns or variables. And we have pulled out, just those first 10 rows and the first 5 columns. And we could do, an analysis just on that slice of the data frame. Okay, another thing to know about square bracket notation now that we're talking about data frames is that if you tell square brackets nothing, it will assume you want everything. So in this case, we're saying from cell cycle rep 1, we've got the first 3 rows we're asking for, and then I put a comma and I didn't provide any more information. And that's just shorthand telling R, hey, I want all the columns. I'm not going to bother to give you that information. So if you say nothing, it will just give you everything. So if we say cell cycle rep 1, first 3 rows, no information, we get all 5 columns back from that data frame in addition to the first 3 rows. Okay, so another way to subset data that's going to be useful in combination with square brackets is something called $ notation. And $ notation allows us to access specific columns of a data frame. And so, we could access specific columns using square brackets, but there's a nice shorthand, and it's going to come in handy, as I think you'll see, and that is this $ notation. And so once you have a data frame in your environment, you can type the name of that data frame, and then the $ symbol, and then the name of the column that you want to extract from that data frame. So you can access any column, any variable of a data frame by using this $ notation. So we can say name of data frame, and then this you can say this as value of, and then the column name. And so in this case, with this line of code, we're saying from the Alzheimer's data frame, I want all of the age values. I want that age column out. And so let's go do that. And one thing to notice, as soon as I put $ there, now I've got, RStudio is really helpful. It's actually allowing me to just toggle through all the possible columns in this data frame, so I can pick out which exactly one I want. And as you start typing more letters, it's going to just start getting rid of possibilities based on what you're typing. And so with V, it's got everything that starts with V, or maybe it contains a V. And so, very useful. It makes it, you can do a lot of tab completing, taking advantage of that functionality. In this case, I think we said we wanted age. And so we can just run that. And there's all the age values. I just grabbed that entire column right out of the Alzheimer's data frame. And so why is that really useful? Well, so we're going to kind of put everything together here, where we're going to do some subsetting, taking advantage of $ notation and logical operators all at once. So we can go ahead and we can access that age column from the Alzheimer's data frame, and we can combine that with a logical operator and say, I want to know which rows of the Alzheimer's data frame have an age value of greater than 85. And this line of code will give us back that logical data telling us that information, which rows have values greater than 85 in the age column. And so this is really, really useful information, because we can use that then to subset this data frame and grab out just the rows where the observation has a value for the age of over 85. And that, in this case, we could imagine studying late onset Alzheimer's. I only want patients who are 85 or older. And so let's go take a look at that. So we can just say, let's type it again, Alzheimer's value of age greater than 85. And there we go. There's all the logical data that we need to extract just those rows from a data frame. And so how would we actually do that? We would just put it inside of square bracket notation. So here what I'm saying is I want from the Alzheimer's data frame, so I want to use square brackets, so I want to subset something. And what I want to subset out are all the rows where the age is greater than 85. And so this expression here contains that information in the form of logical data. And then, of course, we have to give it some columns, or we could just say nothing. In this case, I'm saying I want all the first 5 columns. All right, so let's see how that would look. So I'm going to say from Alzheimer's, if I could type, I want all the rows where the value of age is greater than 85. And for the columns, I just want 1 to 5. And there's that data frame. So now we've pulled out just that subset of the data. Okay, and we of course could store that as something. So we could call that late onset or something like that. And if we run that, that's going to now create a new object in our environment that contains just those rows where the age is over 85. And you can look and see that indeed all of the age values in that data frame are over 85. Okay, and then things, you can get really fancy. So you can start chaining logical operations together. So you can say, and to do this, we use the AND operator or the OR operator, which is just this, this vertical bar here. And so, what would that look like? Well, here in this expression, I'm saying from the Alzheimer's data frame, I want every row where the age is greater than 85 and the value for gender is equivalent to, so these two equal signs, is equivalent to the character data male. And I want the first 5 columns. So we could just go back and modify that original set of, that original expression we had, and we could say, I also want another condition where gender is equal to male. Oops. Having some internet issues here, so sorry about that. So I couldn't access that site previously. All right, oh great, I got an error, and that's wonderful, because here's a really common error. I used equal instead of the double equal sign for equivalent to. So equal, we weren't trying, equal would be like if we were feeding information via an argument, we would say like file equals, and that's not what we're doing here. We're asking for an equivalency. We're saying, I want the value of gender to be equivalent to male. So you just have to kind of change how you think about the equal sign a little bit. And then, of course, you'll just forget like I just did. And so now if we rerun that code, now we've got this late onset data frame. And there we go. All of the values for gender now are male. So, of course, we would change that to something like male only or something and create that. Okay, to be descriptive. All right. And then here's an example of using the OR operator. So in this case, you're getting anywhere where it's greater than 85 or less than 70. So you can basically get rid of anything in between 70 and 85. And you can imagine reasons for wanting to do that. All right, so let's jump into an exercise. So we're going to use that cell cycle data set, the data frame that we have in our environment. And so imagine that you're interested in genes that are regulating the G2M cell cycle transition. So create a new data frame that contains only the observations from that data frame where cell cycle rep 1, the G2M value is over 40. Okay, and here's just a reminder of the syntax for getting that logical data that you can use with subsetting. And then for part 2 of this, when a gene that regulates G2M is inactivated, it often results in replication errors. And that information is held in the X4N plus column of that data frame. And so try to create a new data frame that contains only the observations from cell cycle rep 1, where G2M is greater than 40 and the X4N plus value is greater than 9. So just get some practice with square bracket notation and using these logical expressions and $sign notation and chaining them together, all by practicing trying this exercise. So take a minute, pause it, give it a shot, and then we'll come back. Okay, so here's the answer to the first part. So in order to do this, we might create a new object called G2M phenotype. And we would say from our cell cycle rep 1 data frame, we want a subset. So we're going to use our square brackets in this case. And then which rows do we want? Well, in this case, we want all the rows where cell cycle rep 1, the value of G2M is greater than 40. And we'll just grab all the columns. So I'm not going to tell the square brackets anything about those columns. So, that would look something like this. I think we're calling G2M phenotype. And we'll just say cell cycle rep 1. And which rows do I want? Well, I want all the rows where G2M is greater than 40. And I want all the columns, so I'm not going to say anything. And then we can look at G2M phenotype, and we could see that indeed all of these values are greater than 40. And we can chain onto that, so we can say, all right, I also want to put another condition. I want them to have a G2M greater than 40 and an X4N plus value of greater than 9. And so we can do that by just using the AND operator and then chaining on another logical expression here. And in this case, instead of putting all of this information, it's a bit of a long line of code, I'm storing it as its own object. And then I'm using that object and putting that inside of square brackets. So, you could have put all of this inside of square brackets, but it starts to get messy, hard to see what's going on. And so just for more readable code, I think in this case it would be good to separate that two, those two lines of code out into their own individual lines of code. Okay, so that's, we know how to create objects. We know what some of these common and useful data structures are. We can do some slicing and dicing with square bracket notation. The next big topic that I want to get into is the topic of packages in R. And so what are packages in R? So package in R is something that extends the functionality of R beyond what is available in the base installation. And what packages actually are really just collections of functions where all of those functions are centered around a similar topic or a theme. Excuse me. So, you're going to get a bunch of functions all related to something in a package in R. And it might also include something like some documentation. You might get some sample data. Sometimes there's even a tutorial that goes along with it. And so packages in R are the fundamental unit of shareable code. And so you can imagine someone is out there in the R world and they're creating their own functions, and all of those functions are centered around making beautiful heat maps. And after a while, this individual thinks to themselves, these are really useful functions, and I would like to share this with the community, and that's going to get really annoying. And they will take those functions and they will package them up into an R package. So they'll put all those functions into an R package. They might put some help documentation and maybe some sample data, and they will then share that with the R community and make it accessible to everyone. And so good news is we've already been working with packages and we just weren't realizing it. So whenever you start up a session of RStudio in the R programming language, you are automatically getting the base package loaded for your use into your environment. And so these functions are automatically available to you, and they're going to be a bunch of core functions that are things that are really just everybody's going to want. So things like arithmetic operations, things like the C function, setting your working directory, a function called grep that we haven't talked about. But these functions are automatically going to be available to you in your environment as soon as you start up R and RStudio. And here's somewhere where you can go to take a look at some of the most common functions that I think everything from the base package you can find there. Other packages that are automatically loaded when you fire up R and RStudio are the graphics package. So we've worked with that plot function last time. That's automatically available. Things like read.table, things like, and then that's coming from the utils or utilities package. We get things from the stats package, which is automatically loaded, like rnorm, which we've been working with. Other statistical tests and useful statistical functionality all come from that stats package. And whenever we're working with a function, as we saw earlier, if we call question mark on a function, the first piece of information we'll get is actually what package that function comes from. So we could do something like read.table, for example. So let's go and now we'll see down here read.table is in the utils package. Okay, and we can do like the example in the slide and say for grep, and grep comes from the base package. Okay, so that's just that first piece of information that you'll hear or see about your the function that you're asking for help on. And thanks to RStudio, we can always just click on the Packages tab and get a look at which packages are available and currently loaded in our R session. So if we go to Packages, any package that has a check mark has already been loaded into our environment and is available for us to use. Okay, so that's one way we can get a look at that. You can also you can run the command session info, and that'll give you some other information as well as what packages are currently loaded in your R environment. Okay, so that's the packages that are automatically loaded, but what we're really interested in is all of the other R packages that are available to us. So the community of R users is constantly developing new packages for everyone else to use and making them available for everyone. It's really one of the strengths of the R programming language. Many of these packages are housed in a central repository known as the Comprehensive R Archive Network, or CRAN. There are tons of packages available through CRAN. At last I looked, it was over 16,000. Who knows where it's at now? And you should know that CRAN hosts publication quality code. So it's not a development platform. For a package to get into CRAN, it's got to have met minimal coding standards. And so it's going to be something that works right out of the box. So, it goes through a lot of checks and balances so that when users get packages from CRAN, they know they can rely on them and know that they're going to work. And the other thing is that they have to be non-trivial. So they have to be something new that could feasibly help out other members of the community. And so you can think of CRAN as really a giant warehouse that stores all of these useful R packages. And we, as our users, can just go and grab any one of those R packages, bring it into our environment, and start using those useful functions that other people have written, and keeps us from having to write our own functions every time we want to do something new. So just about any topic you can think of, and many you would never imagine, have dedicated packages available in CRAN. So these are just the first 20 packages alphabetically that are available in CRAN that I grabbed. And you can see the first one is useful tools for geometrical analysis used by the Brazilian Geometrics Association. No idea what geometrics is, but there is a package that the Brazilian Geometrics Association has developed, and there are useful tools for it apparently. Here's one that's a little more relevant to us in the biomedical community. A package that's improved false positive control of gene permuting GSEA with absolute filtering. So gene set enrichment analysis is something that we often do in the biomedical community and in bioinformatics. And this is a package that's going to help us control for false positives when we're doing that sort of analysis. So that could be really useful. Here's three, not one, but three packages that will help us analyze accelerometer data. No idea what an accelerometer is, but there are three different packages for working with that data. And then my favorite one is the Acme R package, which implements Acme estimator of bird and bat mortality by wind turbines. So I had no idea that was a thing, but apparently it is, and there's a package available in CRAN that will help you implement an Acme estimator of that. So just to illustrate this point that anything and just about everything you can imagine, there are packages available in CRAN that will help you to do whatever data analysis you are working on. Okay, so that's great. So how do we get access to all of these R packages? So once you find an R package that you're interested in, you can install any package from CRAN by using the function install.packages. And so we'll just need to say install.packages and then the name of the package that we want to install from CRAN. And so it's extremely straightforward. And another wonderful thing about R, it's just super easy to grab these R packages. And so let's do that. So let's grab what's a really useful package from CRAN known as pHeatmap or pretty heat map. And so we can just say install.packages. And then we can feed it the argument, which is the name of the package that we want to grab. And it's going to be pHeatmap in this case. So install.packages, let's do that together. Oops. And we can run that. And of course, I don't have a connection right now, which I keep forgetting. Fortunately, I have pHeatmap installed already, so you can see it here. Okay, so you're going to go through the installation, and what you're going to see is that it's going to go and connect to CRAN, and it's going to download pHeatmap, and it's going to tell you where it downloaded it, which is not any information that you really need to be aware of. And so that allows you now, you've grabbed all of the information in the pHeatmap package and brought it into your what's known as your library. And so that's great, and it's the first step. But there's one more step we have to go through in order to actually get at the functions in the pHeatmap package. And so once we get something into our library, in order to load the functions from that package into our current session, we actually have to call the library function on that package. Okay, and so why is that? So, well, if you're just starting with R, you're not going to have very many packages that you've got in your library. But in my case, and I recently updated R, so I don't actually have that many, but there is a decent amount there. And whenever you fire up RStudio in a new session of R, you don't want all of those packages to be loaded into your environment. that could start eating away at your memory. So what R has you do is it has you tell it when you want to use the functions from a particular package, and the way you do that is with the library function. So we know we want to generate a heat map, and so we would say once we've installed it, and you don't have to install it every time. Once you install it once, it'll be there the next time you open up RStudio. And so you can just say, now I know I want to be using some of these functions from pHeatMap, so I'm gonna get this and load it from my library with the library function. Okay. And so now we can see the checkbox next to pHeatMap, so it's actually been loaded into our environment. And we can take a look. So the actually pHeatMap's unusual in that there's only one function in this package, and it's called pHeatMap. Imagine that. And so we can get a look at how that function works with question mark pHeatMap. And we can see, it comes from the pHeatMap package. This is kind of generally what it does, a little more descriptive of what it does. And then here's all the possible arguments for the pHeatMap function. But what we can see is that the only required argument is this first one. Everything else is going to have a default value. And so in order to use pHeatMap, the only thing we have to provide is the mat information. And so what is that? So if we scroll down, here's a description of each argument. And the mat argument is actually, it says it needs a numeric matrix of values that we want to plot. Okay? And so that's bringing up a matrix. So what is a matrix? So we know we need a matrix, and we've talked about vectors, and we've talked about data frames. So matrix is a pretty simple concept relevant to those, in that a matrix is a two-dimensional rectangular data structure, just like a data frame. It's made up of vectors that are all of the same length. But in the case of a matrix, they have to all be the same data type. So as indicated by the color here, so typically we'll be working with numeric matrices. And so a numeric matrix will have, it'll be made up of vectors that are all of the same length, and they all contain data of type numeric. Okay, so that's what the pHeatMap function is expecting for that required argument map. And so how can we create a matrix that we want to get plotted with pHeatMap? And so we're going to be trying to make a heat map from our cell cycle rep1 data. And so how can we create a matrix from that? So let's go and take a look. And here's a new function that's pretty useful. And we're going to call it, it's called this str, which is short for structure. And so anytime you have a data frame, you can call str on it. And it's going to give you back some useful information about that data frame. So it's going to tell you how many rows, how many columns you have. It's going to tell you for each of those variables, each of those columns in your data frame, what's the data type. And so we can see that the first column is this FBGN column, a fly-based gene name. So this is actually data from the model system Drosophila. And it's got what are these FBGNs. And so that's data of type character in this case. And then we've got 4 columns that are all data of type numeric. And so we could create a matrix from this data frame by subsetting. So if we could just subset out these 4 columns, they're all numeric, that would actually create a numeric matrix. And we know how to do that. So we can say cell cycle rep1. And in this case, we're going to say I want all the rows, so I'm not going to give it any row information. But the columns that I don't want that first one because that's character data. But I do want the rest, so I'll say 2 through 5. And so we can see if we just run that, that gives us a numeric matrix. It's equal length vectors, all of numeric data. And so we can store that as, let's call that cell cycle rep1 matrix. So here's this new object, and it's a matrix. Okay, and so now we can actually feed that into our pHeatMap function. And so if we go ahead and do that, we can say pHeatMap, and then the only required argument is the mat, where it needs this matrix that we want to actually plot. And we'll say pHeatMap, and we're going to plot that matrix. And if we run that, there's our heat map, okay? And we'll be talking about heat maps a lot this semester. And so we can see, here are the data, and they've all been clustered, and we can look for patterns and trends. Heat maps are extremely useful in a way that we will analyze lots and lots of data sets in bioinformatics. Okay. And so that's just an example of, grabbing a useful R package from CRAN, super easy, just use install.packages, load it into our environment with library, use the question mark to learn about one of the functions from that package, and then actually do some subsetting so that we could feed the proper information into that particular function. Okay, and so the last thing I want to do is get you guys started with another package from CRAN called Swirl. So let's go and install this package. So well, I won't be able to right now, but go ahead and call install.packages and grab the Swirl R package from CRAN. And it'll go and make a connection with CRAN, and it'll download that. And then you're going to call library. So now you're going to load the Swirl R package into your environment. And what Swirl does is it's actually a package for R that lets you learn about R right in the console. So right as you're working inside of RStudio, it will take you through some tutorials. And I think they're really good. So I'm just offering this up as another way to get comfortable with R programming for those of you who are just getting started. And so once you call library on Swirl, it's going to say, hey, and then it's going to say type Swirl when you're ready to begin. So then you're just going to do that. And then it'll say welcome, and it'll say, what should I call you? And for me, I said stguest. It'll say, okay, that's your cue to press enter to continue. So then you'll hit enter. And then it's going to ask you to select 1, 2, or 3 and press enter, and it won't matter what you select. And then it's going to give you all these more information about Swirl and things you can do inside of it that you should take a minute and read those. And then it'll say, let's get started. And then you're going to be given options of what tutorials you want to look at. And so for us, we're going to be interested in number 1, so R programming, the basics of R programming. So you'll make selection 1, and then we're going to go and we're going to say that we want to. It's going to say please choose a course, and we're going to choose R programming. So again, number 1. And then it's going to give you finally a bunch of options. And so I would recommend, in order to reinforce everything that we've talked about in these first 2 sessions, is work your way through lessons 1 through 8. I wouldn't go beyond 8 for this class. I mean, if you want to, absolutely, feel free. But I think what's really relevant to 527 is going to be the tutorials that are in lessons 1 through 8. And so you'll see how you work through those. It's going to guide you step by step, and it'll just give you more practice. In addition to the other materials that I mentioned in my welcome message, and these two videos that I'm recording, and then you layer on this, the Swirl tutorials. I just want to give you guys options to practice R, get comfortable with R as much as possible, and to whatever level you want to do that. Of course, there's always a lot of information and courses available online that you could use to supplement as well. There's just a ton of great material out there. So hopefully this is helpful. And I think if you get comfortable with all the topics that I've mentioned here and that are available in the other resources that I've mentioned, that you'll be more than ready for 527 for this fall. So let me know if you guys have any questions. Thanks.